Hello YouTube. This week I wanted to talk about capacitors again, and what I wanted to do is to give an explanation of how they actually work. Now this explanation is going to increase in difficulty with every step that I'm explaining, but the idea is that if you have a certain level of expertise, then you can watch the video up until the point where you don't understand it anymore, and then maybe learn a bit at the end. Or if you already know everything, you can have a little bit of a victory lap. I'm basically going to explain the fundamental physics behind the capacitor, and I'm also going to explain how engineers use capacitors and more practical mathematics. But this video will only be the physics. And if you've already read through Griffith's Introduction to Electrodynamics, then you're probably going to know everything in this video. So let's get right into it. Chapter 0, Epistemology. First thing you should know is that before you were born, there were a lot of people who knew a lot of things, and after you are gone, there will be a lot of new people who have no idea what you have experienced. And that is just the fundamental part of the human condition. And as a scientific community, we have to make do with this ethereal nature of knowledge. As humans, we just have to constantly relearn everything that we know to the new generation. In doing so, sometimes we compact the information that we have, or sometimes information gets lost. And the Maxwell equations are a sort of extremely compacted version of electrodynamics that is easily presented to a new generation to say, look, this is where we got with electrodynamics. When it comes to something like how an engineer learns how a capacitor works, it's a more specialized application of this knowledge that we have in a more general case in Maxwell's equations. So these different levels of abstraction are not necessarily better than each other, and the practical knowledge that an engineer has many applications that a physicist could never apply just by knowing how, from first principles, a capacitor works, for instance. However, it still adds a lot to your knowledge of the world if you can derive these things from first principles, because it gives you a more complete view of what a capacitor is. So what do we mean when we say first principles? Well, science is built up on the epistemological tool called axiomatic deduction. Usually in science, someone thinks, what if all these phenomena can be explained by this rule or this model? And that model is either an axiom or it is deduced from other axioms. And an example of an axiom is Newton's law of motions. Those were posed as axioms when they were written down, and that means Newton just said, what if these are true, and then did some calculations and experiments and verified that they appear to be true. Chapter 1, Coulomb's law. The entirety of electromagnetics can be built up from only one axiom, as long as you also incorporate the more general axioms about motions, such as Newtonian mechanics and relativity from Einstein, to get magnetism out. So there's only one axiom needed for electromagnetics, that is the Coulomb law. In this video I'm going to skip the Coulomb's law to immediately jump to the electric field. The electric field is derived from Coulomb's law. The electric field is the force that a particle would experience due to another particle based on the initial particle's charge. So we divide the force by the charge and then we get newtons per coulomb experienced. The electric field of a point charge is given by this equation. This C is just a constant, and if you're curious, I think physicists often call it 4 pi epsilon 0, 1 over 4 pi epsilon 0, but what you call the constant for a mathematician doesn't matter. It's just a proportionality, and you can choose your unit so that C is 1 and then it even disappears. Q is the charge, R is the distance, and it's squared in the denominator, and then this R with this little hat on it just indicates the direction, and that means it points away from your charge. So if I have a little charge Q, and a point charge is a mathematical abstraction that just says what if you have just a ton of charge concentrated in a single point, which physically never happens. Even something like an electron is always sloshing about in space, so it's never concentrated as a single point. Then this equation says that this direction arrow says that the electric field always points away from our charge. You should imagine these arrows being everywhere. And then this over r squared means that the further away you get, the smaller this charge becomes. And then, of course, if you have two similar charges, the electric field that a similar charge would experience here would mean, so this is our electric field, and it translates into a force experienced by a charge. Let's call this one Q2 for second charge. This could be a different number. And by the way, when we write down something like Q here, we just mean how much charge is there, and it's measured typically in coulombs. So this could be a 1 coulomb charge, or a 10 coulomb charge, or a 0.05 coulomb charge. But it's just a variable to indicate the charge. And then this electric field says that if this is a positive charge, then other positive charges get repelled, and it gets repelled less the further away it is. And it is exactly dictated by this r squared term. So if we have two charges and we imagine the same situation with a charge that is twice as far away but has the same charge Q2 as this one, then the force is 4 times weaker. Because if we increase this by a factor 2, then this gets decreased by a factor 4. So our point charge creates this electric field around it, and if it would be a negative charge, then the direction of this field is reversed. So instead of pointing outwards, it would point inwards. And negative charges also get pushed the other way in the field. So a negative charge would go against the arrows, whereas a positive charge would get pushed with the arrows. And this is how you go from the typical non-quantitative picture of electro, which is likes repel, opposites attract, to a quantitative version. You just have to understand that it's exactly by this r squared term that these forces get weaker or stronger. The next thing I should say is that there are different reverse square laws in physics. One of them is F over m, where m is the mass of the object whose perspective you're viewing, as a function of x from gravity is, of course, large m over r squared times the constant g, big G that is, which is the gravitational force, but then here it is actually minus r, because the gravitational force is opposite to the electric force. The gravitational force has likes attract, whereas the electrical force has likes repel. Now there's no negative mass, and that negative mass would break a lot of physics, so we find it unlikely to exist at the moment. So this minus just changes the direction. And notice, by the way, these two are vectors. So what is a vector? A vector is an arrow. I just had the little arrows drawn. But if you want to represent an arrow mathematically, this is an arrow in two-dimensional space. If you want to represent an arrow in 2 dimensions, you need the arrow's difference in x and in y. So you need 2 total numbers to represent an arrow in 2 dimensions. And we notate that often with, if we have a vector, which sometimes we put a little arrow above. If I want to be consistent, I can do that here. And then a hat is a vector of length 1. So that's called a normalized vector. And if we have a two-dimensional vector, then we can represent that with two numbers. Let's call them v1 and v2, or vx and vy. Oh, and we put brackets around them like so. Or maybe we can call it 3 and 2. That is an instance of a vector. It has two numbers. It says go right 3 times and go up 2 times. So that would be this vector. But if you're in 3 dimensions, you're going to need 3 numbers to indicate a vector. Let's say we have a vector in 3 dimensions and maybe it's 1, 3, 2. That's an instance of a vector where 1 is the x, 3 is the y, and 2 is the z. So what we do then is we need a little axis system. So this is our x-axis. And the reason I'm showing you this is because electrodynamics is very intricately linked with vector analysis and three-dimensional space. This is our y, this is our z. And 1x means maybe here. And then 3 on the y means 1, 2, 3 is about here. So 2, 3. And then 2 on the z is 1, 2 here. So we have to first find this part and then find that part and then go up by 2, and then this would be our vector approximately. And you kind of have to see the depth in it. I wrote it on top of the y, which is not very handy here, but I hope you can see it. And the study of how to describe these multi-dimensional numbers, these vectors, is called linear algebra. It's very fascinating. Unfortunately, we have to go on now, so I can't teach you about linear algebra. I want to give you one more example of a reverse square law. So I haven't taught you a lot about electrodynamics yet, but trust me, this stuff is integral to understanding electrodynamics. So the next reverse square law is actually a scalar, and it's I. It's the intensity of a light source. So if we have our, oh, this should be a vector. So this means you give it a point in three-dimensional space, typically. The x with the arrow. You can also write x, y, z instead of x with arrow. If we have our intensity of a light source, it is the initial intensity, I0, and then also multiplied by 1 over the distance squared. This is a scalar, so no vector. Scalars are just single numbers if you're talking about vectors. So if you hear the word scalar, you should think single number, but in the context of vectors. Intensity is often measured in watts per square meter, for instance. And it's no coincidence that you measure it in per square meter, and we divide here by the square of a unit of length. So what can you imagine with this? Well, you can imagine a light bulb illuminating your room, or you can imagine the light from the sun illuminating a piece of space, or the earth, or whatever. So if you have the sun here, and if you're very far away from the sun, it's a point source, then it will illuminate the area around it with light beams. If we imagine a tiny square here, or a little part of a sphere maybe, that looks very square-like, and we call this distance r, then you can imagine how many sun rays go through this square every second. If we, however, draw 4 lines through the ends of this square, and imagine our little square twice the distance away, so we add on 1 more r, then we see that the same bundle of light now needs to cover 4 times as much area. And that's exactly where our reverse square law comes from. Now this is assuming that the space in between does not capture any of the light. in real space there is actually some light lost due to collisions with space dust and that kind of stuff. Space is not a complete vacuum, and if you're doing astrology, you will sometimes have to correct for this space dust when you're doing measurements of stars. So that's another reverse square law. And one more thing that I have to mention is I said this was a scalar, but it does get influenced by the type of surface that it touches. And this is very relevant when we look at the Earth. If you had geology in high school, you will be familiar with this. If we have the sun very far away and we imagine the Earth here as a round surface, or the part of Earth where it is day, then of course at the polar caps you will get glancing sunlight, whereas on the equator you get straight on sunlight. And the sunlight at the equator is a lot more powerful because it has a smaller area to cover. The way you calculate this is by looking at what's called the normal on the surface of the Earth, often denoted by a little n with a hat, because it is a unit length vector, or a vector with length 1. If we imagine a random surface in space, we can calculate the normal vector if we have a good mathematical model of our surface. And actually every surface has two normal vectors. There's one pointing this way and one pointing the other way. If we want to calculate the intensity, then we have to view this as a vector going this way. And we have to take the dot product with the normal vector. So if we have a mountain, for instance, we can also model that, and this is used all the time in computer programming. If someone wants to make a shader, for instance, if you want to do ray tracing, you need to use normal vectors on your surfaces to calculate bounces and that kind of stuff. And what is meant by a dot product. Okay, so this is the electric field for a point charge. Let's do some calculations to see if you understand this. What the fuck? Say this is the xy plane. Then a vector is always given with two coordinates. You have to have the x coordinate of the vector, which is a number, and then the y coordinate of the vector, which is a different number. So 0, 0 would be the vector that has no length, whereas 1, 2 would be the vector that kind of points like this. In general, of course, electromagnetics is a three-dimensional theory, but we can take a slice of 3 dimensions, so we imagine our third dimension comes out of the board, but to simplify our calculations, we only write these two components of our vectors, and typically our z component will also be 0 if our problem has the proper symmetry. If we have a charge with charge q at the center of our xy plane, then our electric field will point away from this charge and will get progressively weaker. The strength of our field will be, of course, 1 over r squared, where r is this distance, and this distance can be calculated using Pythagoras. So if we have this point here, and let's call this x naught, and this y naught, and this r, then we know from Pythagoras, since this is a right angle, we know that r squared equals y naught squared plus x naught squared. So r is going to be the square root of this squared and that squared. I use this notation x naught to distinguish from the x-axis, but often we will not write this little naught here, and we just know from context when we're talking about the x variable and when we're talking about a specific distance, and we also call it x. So I'm just going to be calling these x and y. If we square this r again, then we get rid of this square root. Now we want to know the direction of our electric field. We know the strength very easily, but the direction is pointing away from our charge, of course. And we write down a vector by knowing its x component and its y component. So we can use the fact that these two are like triangles, and we can define our little angle theta here. Theta, and that's going to be equal to this one. So these two are going to be like triangles, which means that they have similar proportions. This part is going to be the electric component of x, and this is the electric component of y. And the entire length is going to be equal to the intensity of our electric field, which we can easily calculate as E, these bars mean the length of the vector, is going to be equal to C times Q divided by y squared plus x squared. Now we can calculate this angle theta, because this length here is y, of course, and the arc tongue, so the inverse tangent of opposite over adjacent is going to be theta. And the projection of this vector E onto EX is going to be proportional to cosine times theta. So that means that our final field, and I'm going to use a little trick here, I'm going to use that the cosine of the arc tongue of any number, let's call it z, is going to be equal to 1 over the square root of z squared plus 1. In our case, z is going to be y over x. In any case, we're going to find that our field is a vector and has a position of x and y. It is equal to, and the top component is going to be c times q divided by x squared plus y squared, and then we have to multiply this by the cosine of the arc tongue of y over x, which is also y squared over x squared plus 1, the square root of this thing. And that is our x component of the field. The y component is going to be exactly the same, only multiplied by y over x, because you have to take the sine of the tangent. And then this is going to be our vector. So you would of course never want to do this in Cartesian coordinates with x and y. Usually you write it in what's called polar or cylindrical coordinates, where you express it in terms of r and theta, and then it's very easy because it has no dependence on theta. But this is how you would do it in Cartesian coordinates. So one of the most important things about the electric field is what's called the principle of superposition. Now this has nothing to do with quantum mechanics. This has actually been around for 200 years, long before quantum mechanics existed. It's originally from wave analysis or string analysis and spring analysis, as I could find at least. What it says is that if you have two valid electric fields, and a valid field is a field that can arise from some type of charge distribution, then summing these two charge distributions creates an electric field that is the sum of the electric fields. It's a bit complicated when you say it like that. It just means that it adds nicely, basically. So if you have, for instance, and this is going to be a problem that you should try to solve before you see me solve it, if you want to check if you really understand what I'm explaining here. Imagine that you have your xy axis and you have two charges, and they both have charge q, so they are the same charge. This one is 1 coulomb, that one is 1 coulomb, and they are a distance d apart, or sorry, they are a distance d from the origin. And they're both on the y-axis. And now my question is, how strong is the electric field on the x-axis. You don't have to do any points here or here, because then the mathematics becomes too bothersome. I just want to know the strength of the field on the x-axis and the direction. The direction is actually super simple. So pause now, see if you can figure it out. Think about it for a bit. Okay. So this one is pushing this way, and this one is pushing this way. And pause at any moment if you see how to figure it out, of course. The law of superposition says that we can sum these two electric field arrows to get an arrow that is exactly on the x-axis because of symmetry. So we already know the direction, but now we still have to find the strength of the field. And to do that, we can, of course, make a little triangle again. We do that here. So this is going to be r, our distance. And this is a right angle, and let's call this angle theta. Then we know, of course, that the arctangle of theta is d over x. This is going to be our x. And here I am again using the variable x for the same as what the x-axis is labeling. So this length is x until this point. The strength of our field is, of course, going to be 1 over r squared times some other stuff. But we also need to project it on top of the x-axis again, because all the y component of the field gets cancelled out because of the symmetry. And that was just using the cosine. So we already had that in our previous example, only we have to multiply it by 2 because there is twice the charge. So the answer is going to be 2 times c times q, all divided by x squared plus y squared, and that multiplied by the square root of, oh, I made a mistake. I forgot this d changes the distance. So in this case, we are not using y here. So this has to be d squared. And then here it has to be d squared over x squared plus 1. Now this equation actually makes a mistake because it can only be positive, whereas if we are on this side of the axis, it has to be negative. So we have to also multiply it with the sine of x, and that's just a function that is 1 if x is positive and minus 1 if x is negative. And if we plug that into our calculator, I will show you what that graph looks like. Now I want you to imagine what happens if we have a point charge here, let's call it Q, and we have a bubble-like substance, and you can imagine this point charge as an electric charge, but you can also think of it as a light source for this example. And we have this kind of bubble shape that is a three-dimensional object, and it is completely permeable by the field or light, if you're thinking of it as light. That means that the electric field doesn't get changed by this bubble. You can think of it as being very ethereal. Then let's call this bubble omega, and let's think about what happens to the flux of omega. So the flux through an object can be calculated for any vector field, often denoted by this Greek letter, and it is just a number, but to calculate it is very difficult. The intuition is that it counts how much arrows go in. If we imagine our vector field here, pointing this way, away from our charge, of course here it's going to be shorter, and here it will be longer. So the flux is counting how much arrows go in and subtracting how much arrows go out of our shape over here. And you calculate it with omega, with the integral over omega, which we denote like this. This is an integral sign. And then we take our vector field, in this case the electric field, and we take the dot product with the normal vector. And to actually properly calculate it, you need something called a parameterization of omega, which is just if you have a three-dimensional shape, you typically need three variables that range through a certain distance to make sure you cover every point on your surface. And because omega is a closed surface in this case, we sometimes write a little circle around this integral. Now, if you think about what happens if this were a light source, then any light ray that enters the object also has to leave it. And that means that if you count this all together, it's going to be exactly 0. And that's also true for a charge. However, there is one exception. If we would have put our source, and by the way, this is true for any position of the source and any bubble shape as long as it is a completely enclosed shape. However, if we would have put our source charge, our little q here, inside of our bubble, then this would not be 0. Because all the arrows would be pointing straight out. It would always be constant though, no matter where our q is inside of the shape, because every light ray escaping from our source will at some point cross this boundary. One little caveat: if you have your q here, for instance, then it will leave here and then enter here again and leave here again if a light ray were to go like this. But that doesn't change the equation. You can also put multiple charges in here. And so you can use these flux calculations to sort of count up charges. If we put a bunch of charges here and some here, then there's going to be a very complicated electric field around these charges. But if we can somehow calculate this flux, then we know how many charges we have captured if we know the proper constants to add to make this flux work. And these constants are very simple. It's just going to be 1 over epsilon naught that we've seen before here, times the total charge that is inside, so Q enclosed. So that's all the charges that are inside Q. And of course, in case you forgot this, n is the normal vector always pointing out or in, depending on your orientation of the surface. If you change the orientations of your normal vector, you have to introduce a minus sign here. So this is very useful for solving all kinds of difficult problems, but in general it's not very useful. You need a lot of symmetries for this to work, because most surfaces have horrible unit vectors, and yeah, we're going to see a problem now where this is very useful. Okay, so we've seen what we can do with flux, and this is also known as Gauss's law, and it's one of the 4 Maxwell equations. Sometimes you also see it in the integralless form, which looks like this, where because this holds for any volume, you can take the derivative, which is in this case a gradient, and rho is the charge distribution, so that's like the charge but it's smeared out, and yeah, the epsilon is just the same. We're going to use the integral form though, so don't worry about it if you don't know what the divergence is. Okay, so to do a practice problem with, we first have to introduce a new subject, and that is a line charge. So let's assume that we have a wire, like this could be an electrical wire, and it has charge lambda. Um, Lambda here is measured in coulombs per meters. So with our source charge, it just had a specific amount of coulombs, but here you only have coulombs if you first define your length. This is handy if you want to actually do some electrical field calculations with a piece of wire. So in our example, I'm going to assume that our wire is infinitely long. It extends to the top and the bottom, and it's in a perfectly straight line. In this case, we can do some assumptions that will make our calculation a lot easier. Namely, our electric field will always be pointing directly away from the wire if our charge is positive, and if 2 points have the same distance from the wire, this point and that point, then the field is going to be equal. And those are the only two assumptions that we are going to need in order to solve this problem. So first, let's draw an arbitrary cylinder with a radius r away from the wire. Let's call it big R. And that is going to be the shape that we are going to do our flux integral over. So if we think about the cylinder, we can divide it up into three parts. We have the circular part, and then we have these two bottom parts here and here. And the bottom and the top actually have a flux of 0 because our normal vector is pointing straight down or straight up. Since our electric field is going this way, we know that the dot product of two vectors that are perpendicular is 0. So we can just completely forget about the flux of the bottom part and the top part, and we can only focus on the flux of the cylinder part. And there, the dot product is also very simple because the normal vector is just pointing straight out of the cylinder. So it is it's pointing in the exact same direction as our electric field. And that means that since this has length 1, we know that our normal vector dotted with our electric field is just going to be equal to the strength of the electric field. And then the last thing to calculate is the area. Let's say that this is a height of h. Then the area is of course going to be 2 pi rh. So A is 2 pi rh. Our flux integral was just going to be equal to the integral of our cylinder. So that's without the top and the bottom. And of course, on that cylinder, this product is just going to be the size of E, which we've also established. And of course, we also already reasoned that our electric field at the same radius always has to be the same strength. So this volume integral, this surface integral here is just going to be equal to the product of our area with our electric field, because a constant integral is just the product. And we already know our area. Now the only thing left to do is to use Gauss's law to relate this integral with our charge that is enclosed. Of course, the charge that is enclosed is only the charge inside of the cylinder, and that is going to be h times lambda. So we divide both sides by h. This is going to be h lambda over epsilon no, lambda h epsilon no. And we divide both sides by h since this has h, and then we find that 2 pi r equals lambda over epsilon no and E. So now we find that the strength of our electric field can be calculated as strength of the electric field equals lambda divided by 2 pi epsilon 0 r. So if we have an infinite line, then the strength of our electric field doesn't decrease with r squared anymore, it only decreases with r. So far, I haven't talked a lot about electrical components and circuits yet. Of course, amperes are coulombs per second, so these are the same coulombs that we have been talking about. But that is if we consider moving charges, and we are only considering static charges now, otherwise I would have to explain magnetism, and that honestly is a lot for now. Of course, the other important quantity in electrical circuits is voltage. And voltage, static voltage, can be calculated directly from the electric field. But it's a bit different than the voltage you see in a normal circuit, because it only works for situations where no charges are moving. However, we are going to have to use it to understand capacitors, so I'm going to define it now. Voltage, as you know, is always defined as the difference between the potential in two areas. So let's call it VAB, where A and B stand for the 2 points. And the voltage between A and B is equal to what's called the line integral from A to B of our electric field dotted with our line segment. And what does that mean? If you have a point in three-dimensional space, A, and another point B, then you can draw some kind of path between them. And we typically call this path gamma. And every point on gamma, and again, for these integrals we need a parameterization of gamma again, every point is going to have a little tangent vector, and that is L. Or I should call it L hat, because just as the normal vector, this tangent vector is normalized, meaning its length is 1. So using this, we can calculate the voltage between 2 points in space if we know the electrical field. And this voltage is very similar to the one that you see in circuits. It just doesn't hold up if you're using AC. For this voltage to make sense, of course, it has to be the same whatever path gamma we take. So there's an infinite amount of paths between A and B, and every path creates a different integral, but there are some properties with the electric field, that's namely that what's known as the curl, so that you write as this, of the electric field is always 0. And so this property ensures that whatever path we take, whether it is gamma or let's say gamma prime, this voltage is always going to be unique. We also call it path independent. We're not going to do an example yet. Now let's do an example. Engineers, of course, always put the point A, or almost always put the point A at ground. So ground is defined as the point where you start integrating to find your voltage. But physicists often like to put A at infinity. That's maybe a bit strange if you've never seen something like that, but you can very often do an integral from infinity to some point if you have a nice enough vector space. So let's calculate the voltage of a point charge. A point charge has the field E equals, and let's just look at it on this line so we don't have to think about it as a vector. And this goes all the way to infinity, of course. E equals CQ over R squared. Or in this case, let's call it x squared, because this is our x-axis, and we're only on the x-axis. So that's quite easy, and we can just plug in CQ. Let's write it like so. So in order to find the voltage in the point x, we're going to integrate from infinity to x, and we're going to plug in CQ, and then we substitute t here, t squared, minus 2, sorry. Of course, divided by square is minus 2, and then dt, and then t is just a temporary variable. You could have written x if you prefer, It's not good mathematical practice to put x in if you already have it defined here to also put it here. And this, yeah, is just going to be evaluation of CQ t minus 1 from, and then a minus here, and then from infinity to x. And if we plug in t is infinite, we get 0. So this is just going to be, if we plug in x, we keep the minus, so then it's going to be minus cq over x. Or we could have used r also, because we could have used symmetrical, or we could have used radial symmetry, of course, for the problem. And then we find the voltage of a point charge, and it's a bit easier than the electric field. It's also a scalar. It's actually also super easy to go from the voltage as a scalar field to the electric field as a vector field, because the gradient of the voltage field is exactly equal to the electric field. Because here we integrate it and here we're differentiating again. So that's how you define voltage in electrostatics. Okay, it is time to put everything together. First, we're going to analyze the following situation. Say that we have a surface charge, sigma, which is coulomb per square meter. And we actually have a plate that is as good as infinitely big. So you can imagine that this extends very far, or infinitely far in all directions. Then we can use our trick with the Gauss's law again. We know that the electric field is going to always point away, and if the distance is similar, then it's going to be the same strength. So we can make a little, what we call a Gaussian surface again. This time let's make a square surface. So this is going to be our surface of integration, and we'll make it the same length as the other side. So it's going to be sort of like a, what do you call this? I'm sure there's an English name for it, bulk. And it's going to be a distance r away. So this is also r. And then it has an area A. And the shape of it actually doesn't matter. So let me elucidate this drawing first a bit. So remember that this figure here, this rectangular square? What do English people call this thing? This beam. I'm gonna call it a beam. So this beam over here is kind of our ethereal integration shape, right? And this plate here is our surface charge. So this has some kind of charge on it. You can imagine it is dense with electrons, for instance, or the lack of electrons. If it's a metal plate, it could be a metal plate, could be anything. It could also be a plastic plate with just a charge put on it somehow. But this beam is our ethereal integration thing, and we know that we can ignore all the sides of it because the electric field there is going to be perpendicular to the normal vector, so the dot product is 0. So we only integrate over the area, and we find that the integral, and it's going to be a constant integral again, so the integral over the thingamajig dotted with the normal is going to be equal to the area times the strength of the electric field again. And I'm just going to call the strength of the electric field E. I'm just gonna ignore the whole vector part of it. And then the charge that it's captured in here is the same as the area. So it's going to be equal to A times sigma divided by epsilon naught. And we can divide both sides by A, and we find out our strength of the field is actually sigma divided by epsilon naught. And this is a bit strange. If you have an infinite plate, our electric field doesn't decrease in strength if you go far away from it. Of course, infinite plates don't exist in reality, but If you have a tiny plate and you are very close to the plate, it's as good as infinite still, which is like, you have to think about these things in scales. We know our electric field close to a charged plate now. So now we're going to have two plates, one with charge sigma and one with that is very close to it, and it has charge minus sigma. And the distance between these two plates is going to be d. The area of the two plates is going to be a. And this, don't confuse this a with the last a. And you might already see where this is going. If we assume that a is a lot bigger than d, then we can assume that these plates in between them are as good as infinitely big. At the edges it gets a bit confusing, but let's ignore the edges because they're also marginally small. Camera just died. Let's see. Where were we? Then, first of all, notice that the total charge, Q, is going to be equal to A times sigma. That's on one plate. And next thing we can notice is we already know that our electric field from one plate is going to be, of course, sigma over epsilon null. But we have two plates, so we need a little 2 here, because the electric fields work constructively, because this one has a negative charge and this one has a positive. Next up, let's notice that the voltage between our plates is just the integral from one plate to the other, but the electric field is always pointing in line with the integral, meaning that we can just multiply d times e, because our line integral is going to be very boring. Now we have evaluated e at two different points if we remove this d to the other side. And we can say that this e has to be equal to this one. And then we end up with the following equation. This is going to be 2 sigma over epsilon null. And plugging in sigma is q over a. We get 2q over a. Now I'm going to do a lot of rearranging. I'm going to put q here, I'm going to divide by the voltage, and I'm going to put, what am I gonna do? The epsilon and the a go up, and the 2 and the d go down. We should also notice that this q is the charge on one plate, but if I want the charge on, no, it's okay. And now we find capacitance, because capacitance is just charge divided by voltage. One little thing that's a bit weird that I do, potential I write as a V, but voltage is also a V, of course. Sometimes you see people write potential as U to distinguish, but I just use V for both of them. Also, I'm sorry for putting a capital Q here and I used the lowercase q here. This should have been a capital Q. Lowercase q is generally reserved for point charges, while capital Q is charge in general, measured in coulomb, of course. So we have coulomb divided by volt, and that is farad, or capacitance. So our very simple plate capacitance can be calculated by taking the area and dividing over the distance, and then having this constant in front. And that's how you make a capacitor and calculate how much capacitance it has. If you want to do a nice exercise at home, you can think about what happens if you put a few plates in a row like this, and then connect every other plate. So we connect these two and we connect these two. That's something that you often see in capacitors. Or you can calculate what the capacitance would be for a circular capacitor with one sheet that's rolled inside of the other. And often they are rolled in a spiral, but calculating this is quite difficult if you want the nuances of the spiral. I guess there's probably ways to do it. You can figure that out if you want. Yeah, so what I've mostly shown is that if you have this charge, you get this voltage. But the opposite also holds because of the uniqueness of the field. If you have the voltage, you also have to get the charge. Otherwise, the line integral to calculate the voltage doesn't add up. This concludes the fundamental physics part, and next up we can talk about how to use differential equations to calculate how charge moves across a capacitor. So fundamentally, a capacitor is nothing else than a relationship between charge and voltage. For some intuition, if we make this D very big, our plates are very far apart, and our capacitance gets very small. Whereas if we make this A very big, we have very big plates, and our capacitance gets very large. So the larger the plates, the higher the capacitance, and the larger the distance, the lower the capacitance. In newer capacitors, we don't use air between these plates, and there's all sorts of materials that you can do, dielectrics or whatever. But let me show you some capacitors, and I can show you how this fundamental idea is used. So I've already shown this old capacitor once. Its plates are just wound together very tightly. We see it has a capacitance of 2000 picofarad. You can use that to calculate the dimensions of this cylinder and the turns. Maybe if I can get a sharp shot of the turns. Then you can calculate the size of my fingers if you want to stalk me. Then I have this modern capacitor here, and this one is actually also just a simple piece of sheet metal with some insulating material between it. I know because I broke a similar one. Maybe I can break this one also for the video. If I try to crush this one. So having crushed it, so now you can really nicely see how tightly wound this one is. And if you take it apart even further, you can even turn it into confetti. I didn't show it very well because I completely cut it open, but you can see it's just sheets of metal that are layered super tightly together, and they don't touch, of course. Now I also have this super cool capacitor over here, and this is actually a variable radio capacitor, and I taped a pencil to it to turn it from a distance because I had it tuning a radio, but it was too sensitive to my fingers because the skin also has a certain capacitance, and so I had to touch it from a distance through wood. So the way that this one works is that if you turn it, then you see these two these plates don't touch, but they barely don't touch, and they fit together very snugly, and that creates more capacitance if you turn them into each other. But if you turn them all the way out of each other, then there's very few capacitance between them. And this is actually two coupled tunable capacitors. I think that's for a type of bandpass filter, but I'm not an expert on that. So that you can tune on the specific frequency of radio that you want to receive, depending on how you put it in a circuit. And yeah, it's really cool, I think. So if you calculated the area of my thumb earlier, then you can now calculate how much capacitance this variable capacitor should be able to have based on the area of these plates and how many plates there are. But I don't expect anyone to do that. So some closing thoughts before I end the video. I looked up how polarized capacitors work, and it turns out it's with a very small oxide layer. So you've got the metal, and then it has an oxide layer, and then it's dipped in some conducting fluid. Which means that the plates are very close, and that's how they can get so much capacitance. And because it's an asymmetrical material, that's why it has to be polarized. Because the material breaks down asymmetrically, so they do work with very small reverse voltages, but with larger voltages they melt, for instance, and then the conducting parts connect. So next thing is concerning the mathematics that we just did. So what I showed was that if you have two conducting plates or two conducting shapes in whatever configuration, that there is always a capacitance between them, which means if you make a circuit, actually every wire has capacitance between every other wire, but the capacitance generally is so small that you can just ignore it. Really, capacitance is a property of the shape of your conductors, and the same goes for inductance, by the way. Some other capacitors that I didn't show you are, you have the very small ones that you can get on circuit plates, and then there's the ones that get printed on actual silicon by depositing a tiny layer of metal onto a silicon plate. I also didn't really talk about dielectrics and what conductors even are. For that, I really recommend the book by Griffiths. Lastly, I also didn't mention the history of capacitors. So before capacitors were really a thing, people already discovered these things called Leyden jars. Leyden jars were basically capacitors, but they were stupidly inefficient because they had these huge glass separators, and they thought the electricity fit in the jar. But actually, it was, of course, only stored at the edges, where as a capacitor. So about 50 years after the discovery of the Leyden jar, Maxwell formulated the Gauss law, and about 50 years after that, capacitors started really being used in decouplers for telephones and stuff. So the Leyden jars are really not a evolution of the same device. Now we understand how and why they worked. That was the video. Next week, I don't know what I'm gonna upload, but sometime in the future I will upload a video about actually looking at how capacitors respond to AC signals and how all the low pass stuff works using differential equations. And that's going to be super cool, I think. So hope to see you next time. Bye!